This video is about conservation of energy. First off, the word conservation is not one we run across very often, so we'll cover what that means. Basically, it means that something is being saved or it's not being lost. So when we say conservation of energy, that means within a particular system, the total amount of energy we have stays the same throughout all of its movement or whatever happens to be going on with it. In other words, whatever amount of energy we started with will be the same amount of energy we end with, and it'll be accounted for in some way, shape, or form. It doesn't just disappear. If we reflect back on our skateboarder activity, you should have saw that when you start the skateboarder closer to the top, since P equals mgh, or the mass times the gravity times the height, if you add more height, he's going to have more potential energy. Since before he starts moving, he's going to be all potential energy, that means his total is just potential, then he's got more total energy when he starts at the top than he does when he starts closer to the bottom. Mass also affects that. Again, it's mass times gravity times height. So if I start him in the same place, but I have a really large mass, his total energy is going to be much higher than it is if he has a really small mass. And finally, if we look throughout the skateboarder's time on his U-shaped ramp, you can see when he starts at the top, he's completely potential, and his total is right there, the same amount. When he starts to go down, since he's moving, he gains kinetic energy, but since he's closer to the ground, he loses potential. It just so happens he gains the same amount of kinetic energy as he lost potential, still totaling, if you added those two bars together, they would still be equal to the same total energy as you had at the very beginning. And as he goes further down, he's going even faster, and he's got even less potential because he's closer to the ground, but he still has the same total energy. And then when he gets all the way to the bottom, he's no longer got any potential energy because he's all the way to the ground. So P times G times 0 for the height is 0, and at that point he's moving the fastest he's going to move because all of his energy is put into kinetic energy. And then if you continued watching him, you'd see him go up the other side, and it would just be like watching this backwards. And you could watch that all day if you wanted to. So the important takeaway from that is that you still have the total amount of energy that stays the same throughout the whole system, but the energy can be transferred between kinetic and potential. So if we talk about the math behind it, the conservation of energy means that the total energy remains the same, and if we don't lose energy to heat or work, meaning that this is a closed system, we don't have any extra friction that's taking away from our kinetic and potential energy, we don't have any work that's being done that takes away from our kinetic and potential, then we can assume that all of the energy is either kinetic or potential, or it could be a combination of both. If we know that our kinetic and potential energy, or if we know our kinetic and potential energy equations, we can find the energy of a moving object at any point based on its height or how fast it's going, if we know its mass and the gravity on that particular planet, and all those factors put together. In other words, the equation you'll want to have is the total energy of the system is equal to the kinetic energy plus the potential energy. So if you're given the total, and you're given the height and the mass and the gravity, you can find the potential at a certain point if maybe it's a tennis ball falling from a certain height, you can figure out what the kinetic energy is at the end.